So welcome everyone. We're here for the additive manufacturing for the complete product lifecycle with Jesse Lee, president at GoProto, and David Tucker from HP. We'll just get right into it. So introduce the two people here. We have Jesse Lee, he's president at GoProto. He's a 25-year veteran of the rapid manufacturing space. He's been a part of an incredibly diverse product development programs, from early prototyping for products like the iMac in the 90s through high volume additive manufacturing for projects like HP's 580 color printers. Listening to client partner needs, utilizing the latest and greatest array of manufacturing technologies, and working with the best people in the product development and manufacturing community is what Jesse finds most exciting. David is a production development manager in HP's 3D print business. He specializes in production systems and design for manufacturability. He uses pre-problem solving to eliminate failures before they occur by improving designs. He is a trained plastics process engineer and has released over 1,500 injection molds in the automotive, commercial truck, and high-tech industries. So welcome, guys.
Thank you, Kristen. Welcome. Appreciate it.
Thank you.
So to get started, we're going to have just a brief introduction in terms of who is GoProto. Jesse, you want to go ahead?
Absolutely, yes. Thanks for the introductions, Kristen, and thanks everyone for attending. We're excited by the amount of attendees and questions we received, and buzz and excitement around this webinar. So thank you for attending. Quick little summary of who is GoProto and what are we doing presenting here to you today. We're a community of manufacturing processes that allow for quick turn of plastic and metal prototype through production parts. We're a custom manufacturer using a wide array of different tools to help you get your products from concept through finished production and even end of life as quickly as possible at the best price and quickest, I already said quickest turnaround, but best quality. So what the purpose of this chart is here is just to kind of show that we are a full toolbox. We're a company and organization that employs everything from early machining and 3D printing in prototypes and ideation through high volume production. So we have all of these tools at our disposal to help you get through what you're looking to try to do, and then deploy these to help you most effectively accomplish that. So we've been in business for a long time. We've been in this industry for 3-4 decades, depending on our staff. We've had a manufacturing background that really brings a lot of experience to new tools that we're adopting. Part of the point of what we'll be talking through today is additive manufacturing, and so this shows that we have the background in all the traditional technologies, and we've built an incredible amount of process around it that we're able to apply to new tools to help you use them to accomplish your goals faster.
Great. Hey. So we're going to get right into it. This is the agenda that we have for today. As you all know, when you registered for this event, you all had to submit a question. So what we've done is we've taken those questions and we've segmented them into different topics. And they all fall into these different categories. The goal today is we do want it to be an office hours type event. We do want to have people be very interactive and ask questions. You can see that you have a question and answer panel on your screen where you can submit questions. Feel free to submit those questions anytime, and we will try to address them as they appear pertinent to each specific topic. So to get things started, we're going to talk a little bit, just give a bit of an introduction in terms of multi-jet fusion, what it is, why does it matter, and Jesse?
Absolutely. Yeah, as I mentioned in the introduction here, we've got a wide range of tools that we've used for a long time, huge community built around all these different processes. And a bit of a game changer is the new technology that HP introduced in 2017 called multi-jet fusion. And we've jumped into it with gusto. We're very excited about the process. It continues to prove itself time and time again. It's essentially a new, very capable tool to add to the toolbox. So that's a bit about why does it matter, and now some specifics on what it does and why it changes the equation a little bit. It is a prototype. We've all kind of thought about 3D printing in early prototype, early development, R&D, kind of proof of concept sort of phases, but it starts to lose its effectiveness as you proceed higher in quantity or further along in your product development cycle. And this multi-jet fusion process eliminates some of those things and is helping to kind of expand. You'll see in a chart later, kind of expand its applicable steps and phases in the product development process. Why? Because it's fast. It increases speed over other 3D printing technologies quite a bit. It's very efficient and cost effective. It's also a major factor is that it's production grade materials. It's not a it's not a photopolymer. It's a thermoplastic. So it produces parts that you can expect to perform a lot like injection molded or production type processes. It's also very repeatable. Many of you ask questions about tolerances and repeating the results over and over again. That's essential in a both early validation step and then also into production. So having high repeatability is very important, and it achieves that.
Great. So one of the first sets of questions we had was based on essentially the product lifecycle as a whole. What are the advantages of using additive manufacturing for the product lifecycle? How do we integrate AM into the design cycle, and how do we bridge the gap from prototyping to series production? Do you want to go ahead and start with this one?
Yes, yeah, absolutely. So this chart just shows the quantity on the left and phases of product development on the bottom. So vertical and horizontal. Early ideation is kind of where we've thought of 3D printing for a long time. It is what we've used to make parts that you can test for functionality as well as cosmetics. So we've kind of used to that idea. But now it's the exciting thing here is that you're able to produce parts that are very capable strength-wise, cosmetics. We know we can achieve cost targets with this process. So it's starting to expand its capability. So you see here, we've got blue is additive manufacturing. So those are kind of to the traditional technologies, kind of where we've used to been thinking of them. Yellow is the injection molding. And then green is the overlap. Yellow and blue make green. And that area is much bigger and also much taller. So wider and taller than it ever has been with previous technologies alone. They can do some part of it, but this is really adding to the capabilities and to the uses that you might have of this technology. So let's talk about into bridge production. You know, looking at the questions there, how do we integrate AM or additive manufacturing into the design cycle, and how do we bridge the gap from prototyping to series production? So something that has happened before with 3D printing is often that you would need to 3D print your design. You'd get your parts, you'd test them. You could consider them kind of a configuration, because then you needed to then change processes into, say, injection molding or machining, and then carry on from there. So there was kind of a two-phase thing. And now the exciting thing is that you can 3D print your parts early, validate, get through your ideation, and then know that, okay, now I'm going to go into bridge production, or what that means is kind of intermediate quantities. And you know that you can use the same process. So you don't really need to revalidate. It's not as extensive as it would be if it was in production, if you're doing another process to get you to that point. So that's very exciting. There is an inflection point right there that we want to be straightforward. I mean, a big part of our business is that we do injection molding, we do production machining. So as you look at this, at that point, at the bridge production stage, you're going to be looking at what processes might I use, and we'll be able to analyze and go over things together to be able to see what really makes the most sense.
So there's been one question that's already come in that's actually pertinent to this in terms of the overlap. And the question is, and I think we want to focus, you know, again, keeping the focus on MJF capabilities, is can you take an existing part and print on top of it so that you can then kind of essentially combine both technologies, both injection molding as well as 3D printing?
That is a good question. That's the idea of kind of the pause print. And you can't really do that in multi-jet fusion at this point. The technology it doesn't really lend itself well to that. You can in fused deposition modeling or FDM to some degree, but it still has limitations of where the print head is going to hit it. So at this point, you can't really add to it, at least on the plastic side.
You can, however, you can use like traditional welding processes, whether it's hot plate welding, ultrasonic welding, or even adhesives, to have a base level injection molded component and then add on complexity where complexities are required. So utilizing another manufacturing process to marry
that's a great point, David. And also, this is a thermoplastic, so you can do things like heat staking and sonic welding and things that you can't do with one of the photopolymer technologies. You can do that a little bit with SLS, select laser sintering, and you can do it with machining, of course, but not with stereolithography or carbon. So this is an exciting advantage that it has. Yeah, great question.
It is.
Okay, and then David, did you have any other points on there?
Oh yeah, on the last one, it's just really based around, if you're like a large, we see large organizations trying to understand, because they see the impact of additive manufacturing and digitization in general, and they're investing a lot in understanding how the materials relate to their traditional injection molded materials, right? So therefore, it de-risks the process. The
Right.
process and risk of utilizing additive manufacturing to a bridge standpoint. And typically, they start up in the ideation prototype area, and then they realize that these parts work pretty good, look pretty good. They still have to, check all the boxes that things work, but we see slowly things creeping higher and higher up the production tables.
Yeah, exactly. To be fair, that's also happening, say, with injection molding. That's getting faster and better and more able to do things with softer metals, for example. So
yeah,
so this whole thing is tending to progress wider and taller. So it's
and
it's
faster,
exciting,
faster. The points going higher,
yeah, exactly.
Higher sooner, right?
Yeah. So it's an exciting time, and these tools are helpful.
Yeah. So
okay, we'll move on to design iterations and lead times. Did you want to address this one?
Yeah, sure. So I've built a lot of molds in my career, as Kristen pointed out at the beginning of this. I probably about 1,500. And the one thing that you realize is, that the molding process takes a lot of time. It really is an exercise in project management in many cases, because when you look at a timeline, most of it is my tooling. Tooling's being built. It's expensive, and it takes a lot of time. So looking at ways that you can digitize that ends up saving you in the timeline. You can compress timelines, but my only warning is that the first time that you do it, you might not gain that speed that you're looking for, because you still have to learn. Just like we were saying on the last curve, you have to realize and identify how these materials relate to the materials that you're used to using. So the first time through, you might have to go through a development loop 3 or 4 times. But the more that you understand, the more that you gain that reassurance of how the material is going to work, how the process works, you can start accelerating. So just first time through, give yourselves the opportunity to learn, leverage your relationships with great companies like GoProto who understand the process, and just make sure that you get that time through, and that you spend time to learn. But once you go through it, I mean, you can significantly reduce lead times of your injection molds, of your capital. This was a case study that we actually did inside of HP, and we saved a significant amount of time by keeping this as one solid part, not breaking it down into multiple parts to be tooled. We found performance benefits for it being combined. There was a lot of cascading benefits, benefits to it. And then you get a company like GoProto who also does, injection molding. It can do quick turn injection molding with soft tools, and they even have a better value proposition, not even on the injection molding side. So this is just overall combining parts, and is a great benefit of additive manufacturing in general.
So we do have another question, I think, that fits in here. What's the most important step in the AM value chain?
Depends on what you're making. Higher value things have more value in general, so in terms of the value chain, it's like, I would say value is based on economics. So making sure that you pull all the economics levers to get the best price part. That's the one that's going to highlight on the spreadsheet that you're going to take to your management. That's going to, highlight your savings or highlight your wins. So making sure that you have good relationships with your suppliers that supply parts to you, and that you understand, like, well, what do I need to do to get better economics? What do I need to do to get better parts? And just having that good value chain relationship. Yeah, anything to that, Jesse?
Yeah, I would just offer also speed, as you're showing here on this chart. Really, a big part of the value chain is how can you reduce your cycle time in development. I mean, we all know that right now some products are popping up that are needed to help protect us, for example, and so quick development is critical. So really understanding how to use your tools here can help you achieve that speed, and that's an incredible value. So.
Yeah.
Another good question.
So we got a lot of questions on design. These are some of the questions we pulled just directly from the registration, and hopefully we have several slides here now on design that Jesse and David are going to talk through that hopefully will address all of these.
Mm-hmm. Yeah. So I'm a part designer by training, and so I focus on designing parts, but I focus on plastics. I also have a degree in plastics engineering. And going through the process of designing for multi-jet fusion actually made me a better injection mold designer. So my methodology for teaching people how to design for multi-jet fusion, or really design for any additive manufacturing process to start with, is to associate it back to our understandings of injection molding. I used to say that people didn't know how to injection mold when I was designing injection molds, and I realize now most people are pretty good at injection molding. It's just some fine details that we get stuck up on, or that we get hung up on. Going through these next couple slides, it should help clear up some of that. Very clear methodology and how we should be thinking and how we should be going, starting our design process. 3, I like to think about it in terms of changing our thinking. It's like changing the way that when we get a part, we start to assess that part and say, is this a good part? Thumbs up, thumbs down. So if you're injection molding, there's really three elements. And at first, I didn't recognize them, but now I clearly recognize them. It's like when you first look at a part for injection molding, the first thing that your tooling engineer is going to ask you, does this mold open? Does it actually physically open? Do I have draft? Do my lifters move? Really, it's informing you of the mechanics of the mold process. A good part designer designs for the mold, designs for the mold to be opened. And so really it's the mechanics of the process. When you're designing for any other manufacturing technology, you need to start with that same perspective. Mechanically, does that part work inside of that process that you have chosen? So for additive technologies and multi-jet fusion is, identifying the build direction. So recognizing that the processes are anisotropic, meaning my layer height and my pixel size are different. That I want to make sure if I want something in fine details that I put that on my XY plane and build it up in Z. So first thing, identify my build direction. When you look at these parts here, you will notice like on the left hand, my die draw and my build direction are the same. So I want to have crisp details inside my die draw. I want to have crisp details inside my build direction, but sometimes those you end up wanting to move those around. So when I started design, I can look at around and say, well, I have certain thresholds related to the performance of my part that I want to accomplish, whether it's surface finish, tolerances, economics, or even mechanical properties. There's slight anisotropic behavior there. So and I can identify those, and through a design process when you're starting, we should go through there and say, well, like, what are my goals of this part? And once we identify our goals, I can start rotating those parts through 3-dimensional space. Next slide, please. And as I do that, I can start to gauge how I'm doing with respect to my thresholds. So if I look at certain directions, like for instance, like the one on the left, and I say optimize for accuracy, that pin, that's basically that pinion that goes on the right-hand side of the part, that's up and down in Z. If I print that in that orientation, I'm going to have really fine feature details on that. And if that's the goal of my design, then that is the correct build orientation. Now, as I rotate other directions, I'm going to get different outcomes because there are differences to layer height, there are differences to differences to pixel size. And then, on the far right-hand side, I can also just optimize me for cost. Give me the best cost, the ones that fit best inside of a pack, and we'll explain what that means later. Next slide. So the next bullet, after the mold engineer says my mold works, the second thing that they're going to look at is they typically run this thing called a mold flow. If we could do a show of hands, I'm sure everyone would say, I've used a mold before. I've looked at one, really great pictures. What they're looking at when you run a mold simulation is I want to have like consistent experience of the plastic molecule, meaning I want to have consistent pressure experience. I want to have consistent thermal experience. If there's one thing that any engineer should be looking at any mold flow or simulation, is just, do I have a constant wall thickness? Constant wall thickness means I'm going to have a constant cooling rate. I'm going to have constant pressure inside of my tool. Do I have a constant wall thickness? So with multi-jet fusion, same, it's a very similar. I need to look at the physics. If we had a mold flow to run, I would say run a mold flow, but we don't today. So maybe in the future we'll have some sort of simulation, but it doesn't exist today, but I'm sure it'll be out in the future. but it's the same process of looking and saying, as I'm building a part up, I want to make sure I have a consistent thermal experience. So if you look at like a flat box, I think this is the best example. Associate of mine that I work with, Dave Woodlock, we actually created this together, and it's really simple. If I have a part and I place it in X, Y, and I build it in Z, as I slice it, because I'm going to be building layer by layer. Okay, every single layer I'm going to have a different thermal absorption pattern. Okay, I'm going to print it. I'm going to expose it to radiant energy. I'm going to melt it. If those patterns vary from layer to layer, I'm going to have different amounts of thermal energy absorbed. Different amounts of thermal energy absorption will lead to things like warp. Just like you're going to lead to, if I have a thick section inside of an injection mold, it's going to lead to warp. We're going to have the same issue because it still is a plastics process. So I like to say, from a design perspective, how do I engineer those problems so they just disappear? The best problem I want to deal with is one that I can engineer and just get it off the failure mode chart. So that means looking at things that would potentially be flat, and can I dome them? Can I dome them or can I corrugate them? As you see these two different examples, one's with a dome, one's with a corrugation. As you slice those, you're basically splitting up those printed areas off amongst multiple layers. By splitting it off amongst multiple layers, you get a better thermal absorption and less warpage inside the part. And to be honest, you create more rigorous parts. There is no such thing as flat plastic in any process. So by creating geometry, you help plastics better perform dimensionally, better manage strength and loads and all those other types of things too. So looking at domes, looking at corrugations on flat sections is just a good practice to get into, but it will lead to better outcomes on 3D printed parts as well. And then for the last bullet that we had, it's all about economics. So it's like, when we first look, talk about, injection molding again. First, did the mold open? Second is, does it pass my mold flow? The third thing people are going to ask you is, say, how much does it cost? With injection molding, it's all about how much of this press area, like projected area, or the tonnage am I actually using? That's where we're going to have conversations about, press utilization. What's my press size? How many cavities am I going to do? Am I going to do a family mold to optimize my tonnage? For us, and with multi-jet fusion, it's all about packing density. Packing density leads to economics. If you can design for those packing densities, if you can design for the optimization of that three-dimensional space, that's where you're going to pull the biggest lever for economics. And what that means is looking at like small parts and large parts, and looking at all the parts in your project at the same time to get the largest amount of 3D printed content, and then work with your supply chain to understand your economics, de-risk, and get to those levels of economic proficiency and understanding. And so for the slide, next slide, we have a case study on this. It's something that I actually did working on our 580 product, but we basically took 80 parts. And when you think about three-dimensional build spaces, you have the opportunity to basically think of it like an 80-part family mold, where you can make 80 different parts at the same time. And that when you start to get to those kind of numbers, you are seriously taking off and starting to, when you check off that many tools, that's a serious amount of savings, upwards of $2 million in many cases. And so, thinking about how you save from a molding standpoint is just, getting rid of tools and thinking about how do you optimize build spaces to build them all at the same time.
Quick clarification, Dave, just that image on the left is the multi-jet fusion build envelope. And so those are parts nested together. And then the right is the injection molds.
Mm-hmm. The equivalent molds to build.
Yes, exactly. Those are all chunks of
metal. It's difficult to see it. And it's more than just building these. If someone was to, let's say you wanted to trial 80 molds, you're going to spend a lot of time on a shop floor trialing 80 molds. You probably, at least a week with multiple places running those tools for you. With a multi-jet fusion, it's really within 24 hours, you can start analyzing parts. When you start looking at digital processes, that's the benefit of digitization.
Absolutely. Great.
So we have quite a few questions here. And I just want to point out, I forgot to mention at the beginning that there is an option. If there's a question that pops up in the Q&A that you specifically also want to have answered, but you didn't necessarily submit it, you can upvote that question so that we recognize that several people are interested in that question over others. And one other question that just popped up as well is, will these slides be available? This is actually being recorded and it will be available on demand through GoProto's website immediately after this. So feel free to share it. With that in mind, it looks like we've got a couple questions regarding design. I think you touched on it earlier about the pin needing quite high resolution. What is the resolution and tolerances that can be achieved with MJF?
So it's something that you can print, measure, and get better, just like you're printing with an injection mold, or making an injection mold. You'd run it multiple times. You would measure items on it, and you can tweak your design to get better tolerance outcomes. Out of the box, though, I mean, it really comes down to it's like plus or minus 20 microns, and then like I think it's a percentage over a certain length, because different lengths have different. But it's something that you go through an iterative process and go through and measure and get feedback on and improve.
Yeah, that's an interesting question, and we struggle with that as well, because what we're used to seeing is, say, with injection molding, where you can kind of give a global tolerance. Let's say you're looking at plus or minus 5 thousandths or 2 or 3 thousandths, depending on what type of material you're molding. It is a difficult thing to answer with additive, and we strive for those same sorts of tolerances, but you can get dramatically different results depending on your part design and how well it's optimized for the process. So you end up with a bit of an ambiguous answer, but we are trying to achieve plus or minus 5 at minimum.
Just as a little add-on is that if you are interested in a bit more detail on design for MJF, there is a design guide on GoProto's website that you can check out that has some of these details talked about in a bit further, or bit more detail.
Absolutely. And then same thing, Kristen, with the specifics on tolerances. If someone is looking, if one of you are looking for that, you can always submit your files and we can take a look at it and let you know what we can do. Something that's interesting with multi-jet fusion is being that it's right now they're all amide or polyamide based or nylon based materials. They are post-op machinable. So if you do end up with something that is that you want to have dialed right in, you can set it in a fixture and we can machine it to get either bearing surfaces or high tolerance areas for dimensions. We can get those resolved through post-op machining.
So one person as well asked, and I think the next slide actually demonstrates this pretty well, is are you looking to take advantage or tweak your systems to better take advantage of generative design and topology optimization?
That is a good question. Yes.
Yeah, I posted that one. Not just no,
nicely done.
With any of these processes, it's like, you got to think of like crawl, walk, run. It's like, how do you going to generative design, although it's a great thing, you can get a lot of really great performance benefits from it. When you're first starting your design phase, like you have to know how to do it. You have to have the right tools. We find that if people start with learning additive manufacturing and utilizing generative design at the same time, it can actually slow them down. So when we looked at this part, and this is a part that was actually optimized. And it was the case study that we showed earlier, where it's like, I have a cost savings and performance savings from combining parts and producing them with additive. And then when you look at what we did on this is a topology optimization based on a computational fluid dynamics model. So a lot of words there. What it means is look at the flow of whatever the media that's moving and utilize that as your design metric. And then you can design outcomes other than like strength. It's like noise or flow or some sort of other objective I can design for. This area, especially with multi-jet fusion and other additive processes, looking at how do you design for fluid dynamics, like this is a great area for people. There's not a whole lot of tools to be able to do this. There's a lot of experts to be able to do this. It's hard to recommend even softwares that are able to do this. I know that Siemens can do this, but not a whole lot of others. But things are getting there to be able to do this and create these types of parts.
Yeah, definitely. This is I'll pipe in with a little bit. There's also N topology and a couple of others that have really shown amazing promise. And really, this is where I think a massive amount of growth is possible with additive, because to this point, we've primarily been looking at designs that were designed by people who are trained in how to design for machining and how to design for injection molding. There's not a ton of training on how to design for additive, because in the past, you could just make a design that was really cool, all kinds of cool stuff, but there was nothing you could do with it, right? You couldn't really print it in a technology that would allow you to be able to make parts in production. So kind of wasn't really useful. But now that you can make something that, say, can handle the thermal load of this part, it can get hot enough to be able to take on whatever hot air is flowing through there, or be strong enough, live long enough. Then now it becomes something like, wow, I could really use this, and I can take advantage of the optimization. So whether it be like lightweighting is a big deal. You'll see in one of the case study at the very end that making light parts is important. Also maximizing strength. You've all probably heard that elastomers are a developing thing with multi-jet fusion. And so as you're looking to, say, create lattices and things that will help with compression of those elastomers, that area is a big deal for topology optimization.
I've been seeing a lot of people, especially in topology for one, working on the workflow to get there. So it's like, what tools do you pull together, and how do you make it easy for someone to be able to try something new or to try something different? And in many cases, it's the workflow is the gap.
True.
If the technology can do it, but people can't do it. I think texture is probably the one that it's included. Texture is included if you can figure out how to get it on.
It is. It's free. So yeah, that will show in that sample part later. But that's definitely a service that we can help provide and walk folks through.
So one last question on this topic, on the topic of design is, do you have a comprehensive checklist that one could use to walk through for each of the designs to make sure they review all the relevant areas to compare to additive to traditional manufacturing? I can add that there's a chart, again, on goproto.com that compares injection molding to additive manufacturing. And then we're also in development of putting together a decision tree in terms of when it would make sense to 3D print things. But I'm sure Jesse and David can comment on that as well.
Yeah, you referenced also that design guide that we have for multi-jet fusion that will help a lot for general things like how big can I make my holes, how small can I make my holes, like David showed earlier, flat sections. If you're taking a geometry that has multiple pieces and you want to print them together, what the gap needs to be, things like that, that's extremely helpful. So yeah, those resources are available.
And I like this question that I'm looking at them too, so I'm going to steer it. The one, issues with moisture. So from a polymer standpoint, PA12 isn't hygroscopic. It doesn't absorb a lot of moisture. Not compared
like nylon 6.
Nylon 6. Yeah. So, and also with polypropylene, like zero moisture absorption. Those two materials, you can put them in moisture. You can put them outside of vehicles, and as they get wet, they're not going to change mass. They're not going to change properties. Very, very limited moisture.
Great question, a great answer, thanks. So then, yeah, talking about costs, that's obviously, we got many questions. Again, these questions that we have in here are direct copies and pastes from what you all submitted as you signed up. Cost is a big deal. And I wanna make sure that we're not just talking about money here. There are lots of things that equate to money costs, such as time, such as poor design that ends up with a part that fails in the field. There's a lot of things to consider when you think about quote unquote costs. So often our answer is like, well, we can optimize to help you reduce your 3D print part cost, just straight up. If as David mentioned, one of the primary drivers for costs in additive with multi-jet fusion is packing density. How many parts can I fit into that build? If you're going to be making a lot of them, that becomes a big deal. If you can fit 10 more parts or 10% onto the build, you're gonna save quite a bit in your part cost. So you can do that by reducing some of that thermal mass. So we can pack things together, because there's a recommended packing density that if you exceed, you're going to start getting excessive temperature, too hot, so that you end up with warp parts, you end up with degradation of powder, that we end up then having to use more virgin powder, so it drives up your part cost. There's a lot of little subtle things that are affected by part design. So part design is a massive way to answer this. How do we 3D print at a reasonable cost? We can certainly make it better by better part design. How can we lower the cost of production parts? That's really the same sort of thing. So packing density is number one. Well, yeah, I guess let's go through that, Kristen. Good point. Going to the next slide here. This kind of shows, chart on the left is overall product or program investment cost. You've got your molding on the left and then 3D printing on the right. So then on the right, just starting, if you take a part that's just generally meant for injection molding and you just kind of throw it into the 3D printing hopper and say, print me a bunch of parts, you're going to get the blue bar. It's going to be at this cost. But then as we proceed forward, next slide, we start to look at some things like, hey, this is statistical process control. How do we look at improving our yield and reducing the amount of inspection that we have to do? Let's say that we're printing 5,000 parts. And we know that we have to take 5 dimensions on every one of those parts if we're not confident in our 3D printing process. That is a lot of time. That's someone sitting with calipers, sitting with our digital inspection tools, going through, if we're adding 3-5 minutes per part times 5,000, divide that by your shop rate, you're going to drive your cost up a lot. So instead, if you can optimize your design so that you have easy inspection, we're going to be much faster and your part cost is going to be much lower without really changing much of anything. It's pretty low cost to make that big advantage. Then design, DFAM stands for Design for Additive Manufacturing. That's kind of a slightly new term. We're all used to other design, but digital feedback on design. This is a big part of our service. If someone is interested in going into higher quantities, we have the idea of, hey, just here's a part, print it. But if someone is really looking, I want to optimize the design, I really want to help drive my costs down, drive my quality up, then DFAM is very, very important, and we can reduce costs a lot there. This kind of talks about that. So looking at the left is a part that's obviously designed for machining. A little bit of basic optimization. You reduce some material, reduce some thermal mass, and then, like the question asked earlier, you add some simulation, you add some topology optimization. We really look at what is that thermal mass and what can we do to reduce it so that we can improve our packing density. If we get a better design like this, then we can add more parts to the build, they print quicker, lower cost. And then here's an interesting concept. Thinking about what David talked about earlier of packing density, we think about things like nesting, which is how many of these things can we fit in the build? How do they fit together to give us the best use of a cubic volume? And that means we can stack parts. We can do things. This is different than injection molding. You got to think about, instead of cycle time of a mold, you're thinking of how many parts can I get? How quickly can I get them done? How many parts? Think of it like a dishwasher. How many dishes am I going to get in that dishwasher? Well, they're going to be better if I can stack them together. And that's the idea here. So then you see the blue bar on the right starts to be much more equal with your injection molding. And I believe that's the last slide. Something I wanted to mention here before we move on is not just stackability, but on the right, this is an interesting design thing, is that this is a foldable design. So you may be able to make something that is flat or nearly flat, that when you take out, you kind of pizza box it into shape and you make your part. HP had a great example of one that they made that was a 12-inch long part, too long to really fit efficiently with a bunch of parts. And what they did is they put a hinge in the middle, and then we were able to fold it over and print them folded. And then when you take them out, the hinge open. So you're much more efficient with the packing density, and you achieve the end result. So some good examples of things. I mean, look at all that cost you can save by being more efficient is the idea of this series of slides.
So we've got a few questions here. If I understood correctly, with MGF, we don't have to deal with tooling, not even down to aluminum prototyping to proto tooling, and we get sellable parts. What would be the comparison with additive versus injection molded parts in this case?
That's a great point. And that is a major advantage of 3D printing. You don't need tooling to get your first parts. Now, I need to put some caution in there, is that it doesn't mean you need no tooling, because you might use some tooling, say for inspection. Part of what we're talking about here, you might actually 3D print a go no-go gauge. So there is some tooling, but you don't upfront need metal tooling to make your parts. You're 3D printing directly from your CAD file. Massive advantage of 3D printing. So even if, as we go back to that graph of looking at quantity and through your design cycle, even if initially you start off making a few parts, you may end up finding that 3D printing is part of the puzzle. It can get you parts super fast with no tooling. Whereas then, while you're waiting for your injection mold tool, if for some reason you're like that, you do want to injection mold them, then it can phase you into the production much better than it ever has been able to in the past. Does that answer that question?
I think that if you're designing additively manufactured parts like an injection mold engineer, you're probably going to have 5x cost. But if you're looking for how do you combine parts, how do you get the value of putting things together, that's where you're going to look at the total value of all those types of systems, together.
Mhm.
Not only am I making the parts, but the assembly time of the parts and all those other things. Additive manufacturing is still more expensive than you know than injection molding on a per part level, but when you look at the total system, there's significant savings. So you have to think at the system level.
That's right. And also your design level of things that you might do, say, in the future. Are you going to be changing your design often?
Yeah.
Are you going to be wanting to do mass customization? Do you want to address a specific customer's needs so that you create a little label pocket or something that allows you to customize your product for a particular client, that sort of thing? A lot of advantages that additive can do without tooling. So then, yeah, we've got about 18 minutes left here, and so we wanted to talk about some possible applications. Now we've just got a slide here, and this is just a general discussion. David and I are just kind of talk through what some of the applications are, and talk a little bit or allude to the decision tree of what would make a good additive part. Which these questions on the left are again from the audience. How do we identify good parts for 3D printing and production? What are the opportunities and limitations of using AM for production parts? And then what characteristics define whether a part should be produced in 3D printing versus traditional methods? So these are kind of distilled down from the series of questions that we got that were all around this. Let's kind of start at the beginning of how do we identify good parts for 3D printing in production? And back to kind of, I guess, David, what you were looking at on your chart is first thing, like thinking about thermal load, thinking about design. I would certainly put very high up in the decision-making tree is volumes.
Mm-hmm.
This is still a process that is best for kind of low to medium volumes. And that means quantities of parts. It's still not, if you're going to make millions of parts, 3D printing is going to struggle to make them fast enough and cost effectively enough. So that's kind of a major one. Then how chunky is your part? How well designed is it for the process? And that could then make it be a great part. Is it something that can be modified so that it 3D prints well, so that you have low thermal load, et cetera? And then physical size really is still something I'd say is a big deal. We can print some larger parts. If you'd noticed at the intro slide, we've got some parts that can be 12 to 15 inches depending on the build orientation, but that ends up taking a lot of space in the build, so they end up being pretty expensive per unit. If you've got a smaller, like palm size or smaller kind of part, that's probably going to be most ideal for the process. Mm-hmm. Is that where you're going to?
I would say, if you need a really deep texture, or if you need multiple types of textures, then definitely an additive manufacturing process is right for you.
Yes.
It's like the thing about injection molding, really great, really fine textures, but those textures have to have draft. Like these images of these types of parts that you're showing here aren't manufacturable with traditional technologies. So
that's right. Yeah, so there's some things that 3D printing can do that make it incredibly useful. This image does show, the same part just flipped over. And so on the left, we have an animal or a leather grain texture, and on the right, we have geometric textures. And we have that whole feature kind of standing proud of the surface with the volume underneath it that you could never injection mold. So if you have a part that can't be manufactured with traditional technologies, then obviously 3D printing is a great thing to consider. It may make it a great candidate for 3D printing. So yes, David, that's right. And then geometric patterns, for example, are really exciting because those are things like you can't do an injection mold very well. You can't send it to Mold Tech, for example, and texture a steel tool with snakeskin, or diamond plate or something that varies. There's all kinds of incredible things that you can do in CAD tools that then can translate directly into a 3D printed part. The other thing that I wanted to show, the reason we have texture on both sides of this part is to show that in a powder bed technology like multi-jet fusion, you don't sacrifice the upward or downward facing surface nearly as much as you do with other support based 3D printing technologies. Like stereolithography that we use in-house, for example, has supports that are attached to the bottom side, and in removing them mechanically when you're finishing the part, you end up kind of sanding off some details sometimes or losing them. So in this technology, you can 3D print in 360 degrees.
Hey, Jesse, one of the questions that is kind of on that same topic is can you talk about the comparison between MJF and SLS?
Mm-hmm. Yeah, it's an ongoing thing. The fundamental difference is that they are architecturally different. One, selective laser sintering is using a laser to hit a surface of a granulated powder, all nylon based, and it sinters together wherever the laser hits. So you end up with only one type of material. With multi-jet fusion, you have it's a voxel-based system where you have a powdered material. You drop a fusing and detailing agent onto the surface of that material, and then a radiant energy passes over, and wherever the droplets have been applied to the surface of the powder, it then absorbs enough heat energy to sinter the material together. So think of it like, a laser system versus like voxels on your TV or pixels on your TV. It's the same sort of idea where you can change the properties of the image or the part that you're seeing on a voxel level, on a tiny level. So you can get different material properties. You can vary things. You can get different types of printing outcomes. So multi-jet fusion just has much more flexibility. I would say that right now the technologies, the way that they're pretty similar, but multi-jet fusion, its basic architecture has got a much longer road, like a much bigger bunch of applications, because they can do different materials, not just polyamide based, which is really exciting. And then that basic technology of applying voxels, you can change all kinds of things. You can also do metals potentially, which they're looking at getting into, and elastomers, and also we are getting better results in general right now with density. Parts are stronger. David mentioned earlier, and isotropic properties. Multi-jet fusion is more isotropic than really any of the other processes, including selective laser sintering, which means that it's stronger in the Z than the other processes. So you get a more consistent part, 360 degrees. That's a huge difference.
Yeah, the main innovation where you see where these technologies are going is they're going from point-based to area-based, from area-based to continuous. And so it's like, that's like the technological change. Multi-jet fusion is an area-based powder process. So it processes on an area level. So therefore, it's like it has consistent build times, whereas the time it takes to build something in an SLS process can vary because it's based on number of lasers, the speed and accuracy of those lasers to trace and fill and raster. And so there are differences there, and those differences lead to like performance differences and materials, and also economic differences due to speed and productivity. It's all that transition. It's like, is the technology point based? Is it area based? Is it continuous? And those are the questions that people, if you're looking to purchase technologies or get parts, think about, ask those.
Great point. And that actually comes back into the cost, for example. Like if you're trying to pack a build with selective laser sintering, you add more parts, and it just means the laser has to then go trace that part. With multi-jet fusion, you add more parts, the print head is going to pass over that area anyway, and whether it drops fusing and detailing agents or not doesn't slow the build down at all. The only thing it does do is add a little bit of thermal mass, so it maybe needs to cool down, or it may affect the geometries a bit. But in terms of speed, it doesn't slow it down at all, which is a fundamental.
It's economics, yeah.
Yeah,
exactly. Economics.
Yeah, definitely.
There's a good question about over molding. I think there's two different questions that are based around that. This is an area that I actually find really interesting. So I'm an automotive engineer, and there's lots of different things in automotive that are over molded, from grab handles to different shifter knobs and different types of things. And you can over mold. If you were to build one mold that's just your soft over mold material, you could over mold any part. Now you have to be concerned, do I have a mechanical bond or chemical bond from that secondary material back to the parent material of the first piece? So does that second material stick? We just released polypropylene, and most TPEs, especially the material that people know is like Santoprene, is a blend of a polypropylene material with rubber materials and plasticizer softening agents. So those do bond to polypropylene because they're inherently polypropylene in nature. So you can get chemical bonds as well, and significantly increase the cost savings and time to market and tooling complexity of overmolded products.
Agreed. Okay, great. So we've got 9 minutes left. So just kind of quickly, just wanted to go through a quick case study, just an example, essentially, of a client that's used multi-jet fusion in a case where they traditionally would have used injection molding, and what has this allowed them to do. And this is something that is based on this small company that is essentially started up based on this idea of 3D printing parts for their production. The same same things can be applied even if you're with a large company and you're within this large company. You're like, well, we're not a startup, we can't do 3D printing. I would say that, well, your development group is a small group within a larger company, so you can consider how can I adopt these technologies to help me address my current needs. So in this case, what this product is a drone-based imaging company. So they design cameras that then need to be affixed onto the drone to allow it to do different types of imaging than whatever comes stock on the drone. So the part on the far right, that's 5 of them grouped together, are the 3D printed parts that we printed in multi-jet fusion. We finished by tumbling, and then we added, in this case, a green dye to make the parts green. So in talking with this customer, we asked them, what is the difference between injection molding versus 3D printing? What did you experience your difference in cost and time? And interestingly, this gentleman is what I'd call a 3D native. He said, I didn't even consider injection molding because I know it's going to be expensive. I know it's going to limit my geometry. I know that I'm then stuck with that design. If I want to make any changes ever, I need to modify the tool, which is going to be expensive and take more time, and I've got to requalify. Whereas with 3D printing, I know I can make a complex geometry. I know I can combine several parts. I know I can make features that I can't make that are injection moldable. And if I want to make changes in the future, like I have 5 different versions to hold different cameras, I can do it all. You can print it all in one build. There's no tooling to change. It's very efficient. So he didn't even think about it, which was kind of a fascinating answer, really. And a big advantage that he has, looking through the advantages on Additive, is he calls us or emails us and or he and his company, they order weekly, and we produce parts weekly. So just in time truly is just in time. He has no inventory costs, very low price of managing his parts. As I mentioned before, he's got his design flexibility. It's allowing for printing parts not possible with conventional methods. Also, he's able to make changes when something else comes up. So he's able to keep his design fluid, which allows him to keep up with the technology. So if the Mavic drone changes or his camera needs to change, he can do so. He can just send us a new file that week, and we're right into printing. It's amazingly efficient and low cost. Someone asked earlier, is it true that I can 3D print production parts with no tooling? And in this case, yes, there is no tooling. We have some basic inspection dimensions that he has designed into the part, which is kind of what I was talking about earlier. Like, he has 3 points that are very easy to inspect so that our inspection time is low and his costs are low. So no tooling. And then lead time, instead of saying 5 weeks to make the tool for shots and then prove it out, we're able to get them in 5 days. Although tooling would be, we can obviously do quickly as well. And then nylon 12 that was dyed green. So great example of a client that's using the technology to his advantage to make parts fast and cheap, inexpensively. So then I think that leaves us 5-ish minutes or so to go through and ask any questions or answer any questions
on materials. And I think,
Yeah.
it's important that we will be doing another webinar in the future, very similar to this, with a bit more focus on materials. But is there anything you want to say about materials in the meantime?
Sure. Yeah. And David, you can answer some too. But there are several materials. I noticed one of the questions earlier was also about filled materials, and there is already all the materials that are available right now are polyamide based. So that's nylon-based materials. So there's PA12, standard PA12. There's glass bead filled PA12, and what the glass beads do is increase rigidity primarily. They don't really, because they're beads, they don't really affect the mechanical strength, although they do help minimize creep a little bit. But they actually end up making the parts a little bit more brittle, but they're much stronger if you have a static load. There's PA11, nylon 11, which is something that I want to make sure everyone kind of knows about, because it's a castor bean oil based material. So it's more environmentally friendly. It also has higher ductility, so it's more flexible. It prints really nicely. That's a great material. And then as David just mentioned, polypropylene is a newly introduced material. I guess I just said that it's all polyamide based. So HP's already proved me wrong on that one.
Oh, semi-crystalline. Yeah.
There we go. Make it broader and it's easier.
Yeah.
So polypropylene, and then advanced elastomers are in process right now. There's some TPU materials. There are others in development that are a little softer. So that's a major area of exciting future growth on materials. And then David, do you have any other?
Yeah, my favorite's polypropylene. So out of all of them, I do like it. I think that one is one that has really great ductility, has really great, you can just, thickness, some good economics to it, gravity.
That's your header on LinkedIn, isn't it?
Yeah, that's right.
That's great. So then, Kristen, you'll wrap it, I assume, but I want to make sure everyone knows that this, what we're trying to do, as I mentioned at the beginning of this with our discussions, is to kind of have office hours close to about every month. This is a community of designers. We have these exciting new tools that we're developing that we want to be able to talk about and share and really make available to you so you can take advantage of them. So this will continue on. So be looking for our posts. Please follow us on LinkedIn. Then you'll see the posts about the new webinars, upcoming webinars.
Yeah, so I guess that's it. So there's still a few questions left. We'll definitely keep these in mind for future webinars. But you also can always email directly at quotes@goproto.com. All those resources we mentioned are on the website, and this will be available. This recording will be available on demand as well. So thank you all.
All right, thank you.
Kristen and David, thank you very much. Appreciate it all. Thanks everyone for attending.